And before I start, a bit of a disclaimer. This presentation is based on my personal experience and my personal opinions. It doesn't necessarily reflect my employer or my previous employers, so if you're going to write about this talk or tweet about it, I hope you can respect that. And what I want to talk about today is fast data systems and what it takes to elevate these systems to become an operational technology that's embraced throughout the enterprise to the point where your business doesn't function or perhaps can't even exist without the technology. And just so that we're all on the same page, I think it's best to start with a few definitions. So first of all, what is fast data? So fast data, it's stream-oriented, where the data is processed as it arrives. And there's this focus on processing events in their denormalized form. And the stream of events is usually continuous and potentially infinite. And it's coming from things like sensors, business transactions, logs. And it's been embraced by some as a move away from batch, where you used to maybe process a day's results at the end of the day. And so they can build applications that are more real-time and more responsive. But the event-oriented nature also allows us to more naturally model the systems around us and build applications that we really couldn't build before. So fast data is essentially data in motion, and it has a time series component to it. Okay, so what's an operational technology? It seems like everybody just quotes this quote from Gartner. It's the only one out there. Hardware and software that detects or causes a change through the direct monitoring and/or control of physical devices, processes, or events in the enterprise. Now, this could be hardware and software for operating a power plant, or a manufacturing line, or a connected car. And with the rise of IoT, this can even be devices in our home, systems providing critical services that we rely on every day. So unlike traditional IT systems, an operational technology is something that monitors or alters the physical state of a system. Now, I'm going to assume that most people in this room are at least somewhat familiar with fast data as an operational technology from metrics collection, monitoring, alerting for servers, applications, databases, and so on in the data center. But I'm also going to assume that most people in this room are not in the data center business. And even if we were, we would care as much about collecting metrics from cooling systems and managing power and water consumption and so on as an operational technology as we would monitoring CPU and network. Most of us are ultimately in the business of manufacturing products or delivering services. This is what the business really cares about. And the servers and services that we're monitoring in the data center are just playing a supporting role in delivering these products. So I'm not going to just focus on the mechanics of processing fast data or building the infrastructure that supports it. I also want to focus on building applications around it. Operational technologies from which we operate the enterprise, driving the products and services that we deliver to customers. And I'm going to talk about this mainly from an industrial context, since that's what I'm most familiar with. But you might see some parallels into other industries that you work in. So just like with the fast data that we collect in the data center for servers and applications, the time series component of fast data allows us to analyze historical trends and look at a system at a point in time. And the real-time nature allows us to seize opportunities as they emerge and react to problems before they occur. But in an industrial setting, the fast data infrastructure can be even more important because it allows us to integrate systems like disparate sources of data from sensors to control systems to business systems, even legacy systems. And when we do that, we can suddenly see our business in full color. And the infrastructure for fast data becomes a uniform and democratizing platform for collaboration, for analysis, and for decision making. You're able to put data in front of smart people that didn't have access to it before. And it becomes an enabler of new insights, opportunities, and even entirely new products for the business. So the presentation is broken into 3 parts. I want to examine 3 things that I think it takes to elevate fast data to be an operational technology. The first are unique considerations around time series data. The second is how to combine asset information with fast data in order to provide context. And finally, how to integrate fast data with other services and enterprise business systems in a reliable manner. Now, fast data is not new. It's been around in industrial automation and control for decades, really. But these systems are highly specialized and often using proprietary software and typically not connected to the internet. So what's changed? These systems are now connected to the internet in what's commonly referred to as the industrial internet. And there's been a proliferation of internet-connected devices. And people are building these systems now at internet scale and on top of open source technologies and cloud services. And with really, really powerful computing platforms at the edge, including a phone in everybody's pocket, we've seen the rise of businesses like Uber and Lyft that couldn't have even existed 10 years ago. And I think of those businesses as controlling physical assets. Before I dive in, I'll just describe the perspective that I'm coming from. So I spent about a decade working in industrial automation and control, software for reliable telemetry collection from industrial equipment, control systems, sensors. I worked on a time series database to store and analyze historical telemetry, and pub/sub infrastructures and persistence mechanisms for sharing telemetry and events among systems. And the past few years, I've been working on distributed systems and cloud platforms in a similar flavor for monitoring, optimization, and control of distributed renewable energy assets. Okay, the first topic that I want to examine is the unique aspects of the time series nature of fast data. So when we're in the data center, data collection is really straightforward. Our networks are reliable. Most services are under our control, even if we have provisioned them from a cloud provider. Data retention requirements are usually pretty short, and we can often stand to lose a few samples without much consequence. So a really typical architecture for telemetry collection in the data center would look something like this, where you have a central agent that's polling various endpoints and storing that time series data in some kind of time series data store. So this is recording things like requests per second, percent CPU, response time, and so on. And it's used for dashboarding and alerting. Another architecture that's common is to deploy some kind of sidecar with the service in order to do data collection. This is actually an architecture that I prefer because it can tolerate network partitions without losing any data. And since we often care most about the telemetry around the time of failures, I think this is actually a better architecture. Okay, so in an operational environment, to contrast with the data center, assets can be widely distributed and often in harsh environments. And we can be communicating over unreliable networks with intermittent connectivity or even bandwidth constraints. And not all of the assets are necessarily even under our control. Someone else might own and operate that asset, and we're just providing, we're just a service provider or providing a maintenance contract. When assets are moving, this can pose real challenges in terms of the cardinality of the metadata associated with assets. And we're often interested in very long retention policies, often wanting to store high fidelity telemetry for the lifetime of the asset. And if we're going to operate our business on top of this telemetry, it must be reliable and it must be available. So to contrast with the data center, I want to look at what telemetry collection looks like in an industrial context. So first off, we don't sample the process directly normally. Usually we're talking about like a PLC, a SCADA system, distributed control system, or maybe a gateway that's abstracting things. And this agent performing the data collection has in-memory caches or even a durable queue of data on disk to prevent data loss during network partitions. And often these devices can sustain a network partition of days or weeks without losing data. The agent might also be redundant in a high availability scenario or have local interfaces so that operators can control it directly. It was very popular to have the time series database where we're storing this telemetry co-located with the process and managed by the operational technology department rather than the IT department. But it's becoming more popular now to write data to some kind of durable message queue with a long retention policy. And this improves reliability because it decouples data collection and materialization. So for example, if you lose a disk in your time series database, you could re-ingest some of the telemetry. And it also allows sharing of the messages. So you may be able to run a primary and a backup time series database or share that same data with a data warehouse or other services. It also allows us to share the telemetry with stream processing services so that we can perform real-time transformations or aggregations, or even build entire applications for monitoring and controlling physical assets that rely on streaming telemetry. And then in IoT scenarios especially, but also just as people are becoming more comfortable with cloud technologies, this infrastructure will now often run in some kind of remote data center or even in a public cloud provider and no longer be co-located with the process. But this also means that now we need to manage these remote communications, and there'll be some kind of front end that manages connectivity and security. Might be communicating it with HTTP, WebSockets, MQTT, or this may even be provided by one of the IoT platforms from the major cloud providers. And of course, this is going to have its own dynamics in terms of message processing and buffers and so on. So given the complexity of this telemetry pipeline, especially compared to what we see in the data center world, a key question emerges, and that's what data were available when somebody made an operational decision. In order to answer this question, it can become really important to track the ingestion latency, and that's the time from when the measurement was sampled to the time when it was first ingested. And this can be a key metric to track. And it also provides a time index if we want to rewind in time and reconsume messages. And just because the data have been ingested doesn't mean that they're available for query. So tracking the time to when they're available for a human or an algorithm to make an operational decision is pretty important. An operator may be making a decision based on the temperature or pressure measurement, but could make the wrong decision if measurements are delayed in processing. So we want to represent this uncertainty in the telemetry to the operator. And this can be impractical to track these latencies for every series in your system at scale, but for a few key metrics, this can be really important. How we perform streaming aggregations or joins can also have a big impact on operational decisions. So we need to, anytime we do this, we need to decide what the window is for the aggregation. And of course, we also need to decide when to trigger the aggregation. And that might be based on time, or it might be based on some kind of watermark. And we also need to deal with late reporting data. So it really comes down to balancing these competing tensions in terms of correctness, latency, and cost. And it's about making trade-offs, and I think making those trade-offs somewhat explicit throughout the system. If you're not familiar with all these challenges, I encourage you to read these two essays by Tyler Akidow that are really excellent in kind of elaborating on all the edge cases that you can run into and some good architectures for handling them. Okay, what about revising data when it's being used for making operational decisions? So being able to go back in time and reconsume messages provides a lot of operational flexibility. And this works really well with idempotent databases or services, but it needs special consideration if we're deriving metrics like that ingestion latency that I just mentioned, or if we're joining series, or if we're enriching series with metadata from other services that might change over time, and we would get different results. We also need to consider anomalous measurement, so like a faulty sensor measurement or something entered by an operator that was incorrect. You need to consider if we can filter these messages out on ingestion. Often the answer is no, because you want to study them. But if you're in a regulated environment, like under environmental protection regulation, or you're in pharmaceutical manufacturing, the answer is almost certainly no. You might be able to annotate a sample and display it on a visualization differently, or perhaps even exclude it from a calculation, but the original data must be recorded. And so providing this kind of flexibility in a time series database or in a streaming platform can be really challenging. It's also important to consider how time changes at scale. So with a small number of assets, it's usually quite easy to manage them. But with thousands or millions of assets, as your system grows, you might be processing larger and larger volumes of data. And this can impact system dynamics and latency in ways that you didn't originally anticipate. So you need to consider this in the design and have strategies for sharding or scaling out and maintaining your SLAs as you scale. And of course, with thousands or millions of devices, inevitably some are offline, some have incorrect clocks, some have firmware defects, some have software defects. I've seen devices reporting data way into the future when they should be reporting in near real time. And my personal favorite devices continually uploading the same samples from a few months ago, over and over and over again. And this can have big consequences in a system. So say you're storing that data in a time series database and those files get compressed. You might be continually recompressing those files and consuming a lot of resources. You also need to consider data that's late arriving. Can we recompute calculations to make them complete, or do we need to retain the original measurements because that's what an operational decision was made on? And I think often the answer is both. We need to retain a measurement that someone or some algorithm made a decision on top of, but we also want to recompute the calculation so that we have a complete picture of what happened at the time. So the management of all this uncertainty really comes down to implementing it in business logic. And it's okay for these systems to be eventually consistent or the telemetry to be incomplete, but we need ways to represent this uncertainty, embracing the uncertainty in the data model so that we can communicate it. And we often need logging as part of the ingestion pipeline in order to identify these exceptional behaviors, and business logic to enforce expected behaviors and protect server-side systems. It can also be really advantageous to just have this business logic server-side in order to compensate. Because if you have millions of devices and you have some kind of firmware defect, you can't just necessarily update those overnight, especially if they're in, say, a regulated environment where you need to revalidate. So being able to compensate server-side is pretty advantageous. Okay, finally, we're often not just interested in a measurement at a specific time, but a measurement that has a start time and an end time, some kind of time frame. And these can be dynamic events like a control variable excursion, or a discrete event like a set point change or a battery charge and discharge cycle. And time frames become really useful for providing context to the underlying time series data. And enable things like, find me all of the control variable excursions on the manufacturing line that began and ended last week. Might also want to associate metadata with a time frame, like who changed the set point and why. Now, a lot of us are probably familiar with web applications that have relative time frames in the URL, and this allows us to share a URL with one of our colleagues and put them into the context that we were in. So this is useful. And this is an example from Grafana where you can annotate a time window. So here, annotating the control variable excursion with a tag and a comment. And I believe this is stored in the Grafana annotations database, and it's dashboard specific. So if you copy the dashboard, the annotations don't come along with it. So this is the right idea, it's the right flavor, but this needs to be abstracted so that it's available more ubiquitously throughout the system, because we want to leverage this across visualizations, not just in Grafana, and we want to generate reports from those timeframes, or even drive stream processing applications from the same timeframe. Okay, to sum up the challenges around time series data and in elevating fast data to be an operational technology, you need to consider a lot more than just sample time. You need to consider latency, whether we can modify samples or delete samples. Time frames emerge as being very useful for providing context to the underlying time series data. And we need a lot of investments in the ingestion pipeline in terms of business logic, investments for reliability, scalability, and providing insight into unique behaviors. Okay, part two. The area I'd like to focus on next is how we take asset metadata and asset models and integrate that with fast data in order to provide context. So in the data center, again, providing context is usually pretty easy. We can associate metadata at the time of deployment, things like the application name, the cost center, the data center. And we can use kind of a tagging approach. And it's declarative and it doesn't change. But just like we saw with time, incorporating asset information is much more challenging in an industrial setting. So to start, what do I even mean by an asset? And this really depends on your perspective. So if you're operating or scheduling this aircraft, then you probably view the entire aircraft as your asset. But if you just have the maintenance contract on the engine, you probably just view that engine as the asset, independent of the aircraft that it's installed on, or whether or not it was late arriving from Toronto yesterday. So consider a steam turbine that's defined by these 4 core measurements: the flow rate, temperature, pressure, and power. what does it mean to be a steam turbine? It really depends on your perspective. So if you're an operator of that turbine, you might care about those 4 core measurements plus the set point. But an application running models for condition-based maintenance might care about the 4 core measurements plus vibration, faults, and the runtime. And so in a programmatic sense, you can think of this like a compositional model, like mix-in traits or interfaces, providing different views of the asset depending on your perspective. Now, in addition to being interested in how a single asset is performing, it's often important to understand how a group of assets performs in the aggregate. And this often leads to parent-child or hierarchical relationships. So the lowest level here might be a wind farm, and then the next level would be something like a county or a province or maybe an interconnection. And then the top level group would be something like an energy market or an asset owner. And often we want to include assets in multiple groupings. So you might want to group by geography, group by customer, group by the capabilities of the underlying asset. And sometimes you can manage these asset models with tagging, like I was describing with the data in the data center. But tagging really breaks down when you start making group by queries, because group by really only groups by what is there and doesn't really describe assets that are offline. Because in an operational setting, you want to make statements like, these set of wind turbines are producing 57 megawatts of power, but only 19 of the 20 wind turbines that we would expect to be reporting telemetry have reported. So representing that uncertainty. I also want to be able to navigate these asset models in user interface applications and so on, and that doesn't really work so well with just tagging and using group by. It's also important to consider how these assets are changing over time when you're modeling them. So today, your asset model might look something like this, and then tomorrow you bring more assets online, and then even later you bring even more assets, and perhaps you even rearrange the groupings. Now, if you're looking at historical telemetry or making historical aggregations, you don't want the current asset model. You want the asset model that was governing at the time. And so what this really means is that all data is time series data. It's just kind of the nature of the relative timescales that's changing. And this brings a time series component to the asset model itself. Assets themselves also change over time. We tend to think of them as static, but they're not. Parts wear and they're replaced. The ownership of the asset changes through acquisition. This can bring up issues with lineage and custody of data. So let's say you buy a house that has a solar installation on the roof. Can you see the telemetry from before you bought the house? Or is that private and managed in the asset models through some kind of effective date? And what if you replace the internet-connected thermostat in your house with a newer model? Can you seamlessly see all of the old telemetry from the old thermostat, or can you only see it from the new thermostat? And what this really comes down to is not all of the metadata around assets is available at the time of ingest in order to use a tagging approach. And even if it was, re-ingesting data at scale in order to adjust tags is really just unworkable. So you need asset models that are more flexible to changes. There's also a security component to these asset models. And the first is just kind of an inventory of what you're even running. You can't even start to assess your risk if you don't know what you have running. And then back to the polymorphic views of the asset I was describing earlier, it's common to need role-based security around these views so that you can only see the series that are appropriate to your role, and using a, say, database-level security is just too coarse. And role-based security is also important in these asset models that are kind of hierarchical, because often you might be able to see telemetry or maybe control certain assets but not other assets, and that needs to be expressed and enforced through the asset model. Lastly, it can also be important to understand directional relationships in physical systems, so chemical systems, mechanical systems, electrical systems, understanding what's upstream and what's downstream. So consider this piping and instrumentation diagram for an oil refinery. I'm just going to zoom in on a single pump and a single heat exchanger. Now, the mass flow rate out of this pump is equal to the mass flow rate into the hot side of the heat exchanger. It's the same product, it's the same units, it's the same direction, it could even be the same underlying telemetry. And so if you think of this from a programmatic perspective, you can think of it as kind of a strong typing system for the asset model. And it can be used to automatically derive streaming calculations or visualizations. And it also can prevent errors, like you can't connect a kilograms per second mass flow rate output to something that expects grams per second as input. And providing this kind of richness in an asset model it's pretty difficult, actually, but it's really powerful. And I think there's opportunities here for innovation in terms of how we build and operate fast data systems. So to summarize the important things around providing asset models and asset metadata in order to elevate fast data to be an operational technology, we need a heck of a lot more than just group by queries. We need to express hierarchical, directional, proximal, and even temporal relationships. Assets and their relationships are going to change over time. They're not static. We cannot associate all metadata with telemetry at the time of ingest. We need something that's more flexible. And security and role-based access emerge as really important components of an asset model. Okay, the last topic I'd like to explore is how we integrate a fast data infrastructure with other systems. So I already talked about how not all of the asset metadata is available at the time of ingest. That asset metadata and the models is going to come from this alphabet soup of business systems, operational systems, enterprise systems. And these will be the systems of record for this asset metadata and as well as the models. So the question becomes, how do we integrate fast data with these systems? Now, I see it as somewhat inevitable that we have to go and build some kind of asset service that's specific to whatever industry that we're in. And this asset service might abstract these other services and just act as a proxy, but more often than not, it's going to have its own databases and caches to satisfy unique query patterns, and also to deal with the fact that a lot of these other systems can't be exposed at an enterprise level. You'll have some legacy database that has some strange query format. Maybe it doesn't even have security. It can't scale to the level of queries that's required. Or some systems might reside in security contexts where you can't access them. So, for example, you can't access the control network from the corporate network, and you need to reflect this information somewhere else into the business. It can also be, asset service can also be crucial for auditing data quality issues, like identifying assets that are missing addresses and this kind of thing. And this is really not a solved problem in my mind. I think there's a heck of a lot of room for innovation in this space and creative thinking on how we integrate all these systems in a more uniform manner. So just to provide an example of how the asset service would be used to, say, query historical telemetry, first, you would navigate your asset models and resolve some kind of unique identifier that's stable, like a device ID, a serial number, an address. And then you would use that to query the time series database to resolve the underlying telemetry. So this gives a really rich asset model that has a lot of flexibility, and you can leave the telemetry as essentially immutable. And this could be done by the client, or you could abstract this all up into some kind of time series service that provides this unification. Now, of course, streaming services are also going to need to access this asset service to do data enrichment, joins, aggregations. And sometimes there's no way around it to just connect the streaming service and the asset service together. But this does tightly couple those services. And this can be really dangerous when we want low latency and highly available telemetry ingestion. Of course, the streaming service could cache some of this asset metadata, but then that needs very careful attention in terms of sharding strategies, scaling strategies, and cache invalidation, and all these hard problems. So it can often be more advantageous for the asset service to publish changes, say to that durable message queue. And this allows streaming services or even user interface applications to react to these changes in near real time. But to scale these services infinitely and reliably, we really need to make the business logic independent of scale. And I already mentioned that it's not possible to associate all of this metadata at the time of ingestion, but rather than enriching events later on, if you can push as much metadata as possible to the edge, it's advantageous in that enriched events are easier to deal with because services can act independently on the same view of the data. And so you could have software at the edge, say, negotiate metadata with the server to make processing, partitioning, routing, aggregation easier. Another big challenge in integrating fast data with all of these other systems is representing the expected state versus the desired state versus the reported state. And this leads to a lot of data quality issues, like what the customer ordered isn't necessarily what you installed. Or you might be relying on, say, capabilities of the firmware, and the device is running an older version that doesn't have those capabilities. So there needs to be a clear delineation between expected, desired, and reported state of the metadata. And I think anytime you're making operational decisions about the capabilities of the asset, like what's the amount of power that it can output, always favor the state that's been reported by the asset itself rather than something that's in some business system. Okay, so how do we integrate all of these systems in a reliable way? I've talked about a lot of different systems, from sensors, complex ingestion pipeline, this asset meta service tying all of these other services together, business systems, legacy systems. And I don't just want to integrate these systems together. I want to build technologies on top of it for monitoring and controlling physical assets. And to be an enterprise platform or an operational technology, these applications must be reliable, they must be robust, they must be scalable, they must react to changes in near real time. If you're going to build a platform for, say, bidding those wind turbines that I showed into the energy markets and your real-time telemetry is not available, well, then you could be losing a lot of money. So I think there are two important things to consider in integrating all of these systems together in a reliable way. And the first is the ideas that are in the Reactive Manifesto, I think a large reason why we're all here at this conference. And those are the ideas of embracing events, embracing eventual consistency, explicitly embracing failure in the design of systems, and embracing loose coupling among systems. Now, reactive systems rely on asynchronous message processing, which makes them elastic, which is responsive under load, and resilient, which is responsive under failure. And this message-driven, eventually consistent structure is just perfectly aligned with these fast data systems. And also, when we embrace events, we naturally construct systems that embrace these principles. If we model events, we model behaviors of the system rather than the structures of the system, and this leads to really good designs. And the second thing that's important, because these systems are event-oriented and the data is constantly in motion, we need to guarantee resource constraints to protect the integrity of the system and improve reliability. So some systems do this crudely by applying back pressure through polling or blocking. But Reactive Streams protocol is a set of interfaces for implementing non-blocking flow control. So instead of the upstream producer pushing data to downstream systems, the downstream, and potentially overwhelming them, the downstream system requests demand from the upstream, and this can be done batched and asynchronously, so it can be quite efficient. Now, a lot of people get really excited about Reactive Streams protocol, and this is an example of part of the specification for the subscriber. But this is really intended as a service provider interface. This is for library developers. Application developers should be using a high-level Reactive Streams library, because we want to do things like mapping, filtering, throttling, merging data streams, partitioning data streams, or buffering samples in memory so that we can have efficient writes. We want to do things like limiting asynchrony or handling error conditions with backoff and retry. And so this model fits really well in kind of a functional style of programming across collections at a higher level, with the Reactive Streams protocol itself taken into consideration by lower level libraries. Now, and these ideas are really conceptually trivial, like throttling is conceptually trivial, but it's difficult to implement, especially for unbounded streams of data. So what does it look like to actually implement these systems? And I think I should start by discussing how we actually avoid creating a house of cards. So this is a recent XKCD cartoon. I'll let you read it. I think there's a lot of truth in this cartoon. Okay, so it's pretty common to see pictures like this in presentations, blog articles, and so on, where you just connect everything to Kafka, and boom, reactive systems, fast data, so on. I think actually this conference was even criticized the first year for too many pictures like this. Now, and don't get me wrong, this is certainly an improvement. Having some kind of central, robust platform for messaging rather than a spaghetti of one-to-one connections is a huge improvement. And if you're doing things like enforcing schema and so on, the system gets even better. But to me, it's not about moving data from A to B or performing simple transformations and connecting things together. What I'm talking about is building applications that monitor and control physical assets. And the real challenges here lie in the things that I've already talked about. So dealing with data quality issues, providing some kind of consistent and unified asset model, and representing uncertainty in telemetry. And often the challenges lie not in connecting things together, but in the connections themselves. Like how to represent failure and uncertainty many times needs to be an application level decision, not something that we get by magic just by putting a service mesh on top of this. So Kafka is just a tool, and it's a great tool, but building fast data systems as an operational technology requires an array of tools and not just the adoption of one technology or another. So to me, building these systems comes down to these fundamentals. These are the building blocks that personally I want. The first is something for managing state. Because I want to model the state of an asset. I want to model what the current power output is for one of those wind turbines. And I want to model what that asset's relationship is with other assets. And I also want to model with state machines. Like, is that wind turbine online or offline? And have different behaviors for each state. And I also want state machines for modeling workflows. So when I'm commissioning new assets, or if I want to reliably send commands down to an asset and deal with acknowledgements, I want to use a state machine approach. So I know that these systems are going to be larger than the memory, CPU, or I/O resources of any one machine. So that means we need to distribute these workloads. So I want something that will model assets autonomously and run workloads concurrently. And because computation is going to be distributed, we need messaging that embraces location transparency and failure and error handling as part of the model. And I want to be able to message with this huge array of other systems like I've talked about through this presentation, and not just in request-response patterns. And finally, I want APIs that can deal with the large volumes of data in motion, and I want these to be expressed in streaming semantics. Okay, so what tools provide these building blocks? My preferred tools are actor model programming for encapsulating state and executing state machines, as well as modeling assets themselves in kind of a digital twin representation, and also for modeling workflows. And then also using actors as the unit of computation that can be distributed and executed concurrently. And then messaging to interact among actors, but also to this wide variety of external systems. And I want first-class messaging that's not just request-response, but I want tools for two-way communication, for publish-subscribe, for server push, so that services can react in near real time, or tools for interfacing with message queues, or even just streaming huge data sets. And I want tools for interfacing with a wide variety of systems, or even protocols like MQTT, AMQP, or OLE for process control. And then to deal with this data in motion, the tool I want is reactive streams. That's going to give me back pressure and resource constraints. But I want a high-level reactive streams library for expressing these high-level patterns that emerge so often in fast data systems. So if I was looking to explore something new, I would be particularly interested in these projects. I'm not familiar with any of these technologies. I've never used them to build a production application. But I think all of them tick the boxes in terms of distributed actor model programming, and all of them have some kind of streaming component. My personal favorite, and I think it's fair to say the most complete ecosystem as well, is Akka. So Akka is an actor model toolkit with distributed computing components. It has APIs in Java and Scala. I think it even has a port in .NET that tries to maintain parity. My preference is Scala for functional programming. And Akka has a high-level reactive streams API through the Akka streams. And then it also has rich messaging. So Akka HTTP will provide HTTP clients and servers, HTTP2, server-sent events, WebSockets. And I think an area that Akka really, really shines in terms of messaging is the Alpaca project. And this is reactive streams libraries for interfacing with a huge variety of other systems, and doing so, following the reactive streams specification. And I think it's also important here that it's not just, say, a connector from A to B. It's an API that you can use to build applications, which is really what I want. So I'm excited to see here the recent drive to Alpaca 1.0, which is trying to have APIs that are more consistent. And this has always been a community-supported project, but now there's actually paid full-time staff working on it, who I believe are at the conference. So be nice to them. I think if you take a step back, actually, and look at functions as a service, I think they're evolving to have these same building blocks, if they don't have them already. So you can think of the function as the unit of computation that can be widely distributed, can act autonomously, they can be run concurrently. You interact with functions either via messaging or giving them immutable data sets to work on. I think Microsoft Azure actually recently released durable functions for managing persistence, checkpointing, and replay. So I feel that functions are really evolving to provide these same tools for building these kind of systems. It's somewhat interesting if you want to embrace functional programming, which I think is the inherently obvious way to build these systems. I think the only choice is F# on top of Azure at this point in time, but I would expect that to change. Okay, to summarize the important things around integrations in terms of elevating fast data to be an operational technology. There's going to be many systems of record for asset information. Building some kind of asset service, I think, becomes somewhat inevitable, and you're probably building an asset service that's specific to your business. We should embrace reactive systems and reactive streams for integrating services in reliable ways. And I think embracing these building blocks, a distributed actor model programming, first-class messaging, and some kind of high-level reactive streams library are the right tools for building these systems. Okay, those are the three topics that I wanted to cover. I'll give my main takeaways from the entire presentation, and then I just want to provide some concluding thoughts that go beyond technical considerations. So first of all, time is multifaceted. As we saw, we need to consider a lot more than just the time that measurements are sampled. The ingestion pipeline requires a lot of investment in terms of business logic. We want to provide asset data and models for providing context to fast data. And the asset data is going to come from many, many sources, and it's going to change over time. And this means we need to integrate fast data with a huge array of other systems. And we should embrace reactive streams, reactive systems, so that we build these in a reliable way. And I think some kind of unit of computation, messaging, and reactive streams are the tools for building these systems. Okay, to conclude, in building these sophisticated and sometimes complicated systems, like some of the overarching challenges aren't just technical challenges, they're systemic challenges, they're organizational challenges. And I think the first is there's not enough people experienced in building these systems. I think the people in this room are perhaps somewhat unique. So there's a lot of people out there with experience in industrial automation and control, but without experience, say, in building distributed systems or cloud-native systems. And it also goes the other way around, where there's lots of people out there with experience building distributed cloud-native systems, but lacking experience in industry, manufacturing, critical infrastructure, regulated environments, these kind of things. I think many organizations struggle with technology decisions and implementations. But at the end of the day, it's really not about building these systems is not about adopting one technology or the other. It's about adopting the right mindset and laying the foundation for these systems. And I think a lot of organizations struggle with short-term expedient thinking, and this leads to systems that are poorly engineered, brittle, unreliable, and in some cases even unsafe. So some things that I think will help this, first is maturing our tools and our platforms. And I think in doing this, we're going to start to constrain the choices that need to be made and encourage good decisions. I think you can already start to see this, say with functions as a service from the major cloud providers. Your choices are somewhat constrained and lead you down a good path. also think it's really important to embrace systems thinking and to focus on the quality of our work. Reactive Summits put a lot of attention to diversity and inclusion efforts. As Kiki mentioned, there's a panel discussion on this tomorrow. And I think one of the reasons this is important is systems thinking. We want a diverse array of perspectives from the people in our teams in order to take a systems approach to problems. And it's my personal opinion that one of the hardest things for individuals and teams is embracing people that think differently than them. Maybe that's a thread that the panel can pick up on tomorrow. And finally, in order to improve systems thinking and the quality of our work, I believe one of the most important things we can do is elevate software to be an engineering discipline. And I think the systems that I've talked about today are going to be at the kind of the intersection of this change happening to the industry. And the first reason is that operational technologies are operating critical infrastructure or service, so there's safety concerns or providing services that people rely on every day. So there's going to be safety and reliability aspects that are going to require the ethical rigor and the technical rigor of an engineering discipline. And I think given the complexity of these systems, especially at scale, operating these systems will look like process engineering or systems engineering, and we'll be taking empirical approaches to monitoring and controlling those systems and controlling data flows. And it's going to look a lot more like operating an oil refinery than it does operating a SQL database. And I think for these reasons, reactive systems, fast data systems, software as an operational technology will be at the heart of this transformation in our industry, elevating software to being an engineering discipline. Okay, if you want to keep in touch, that's me on Twitter, and that's my blog. I try and write one essay a month on software, engineering, teams, these kind of things. If you want a bit of what I said here today in written form, this is my suggested reading list. The first two articles there talk about these ideas of fast data and time series and using it in an operational context. And the last three examples are around Akka and Akka streams, and they'll give a flavor for why you might want to use a high-level reactive streams API and how you might integrate it with actors and do actor model programming with it. Okay, so that's it. I'm looking forward to a great conference. I'm really excited to be home in Canada. I'm personally looking forward to the talks on RSocket. I think there's a talk on actor model programming with Microsoft Orleans that I'm looking forward to. Of course, the keynotes on PhiloDB and migrating to microservices, and the panel discussion on diversity and inclusion that I mentioned. And of course, really looking forward to all of the hallway discussions. So I can try and take a few questions. I may not be able to answer them all. If there's something I can't answer, I'm certainly happy to speak with you after.